Training deep neural networks is fundamentally a battle against a highly non-convex loss landscape. We throw millions of parameters at stochastic gradient descent, tweak learning rates, add regularization, and constantly ask ourselves, what actually moves the needle? One of the most consistent tricks in the optimization toolbox is injecting random noise directly into the model parameters during training. It helps escape sharp minima, improves generalization, and even plays a role in differential privacy and adversarial robustness. But despite decades of research and a flood of recent papers proposing increasingly complex noise schedules, we still don't know which design choices actually matter in practice. A recent paper from Université Laval cuts through the noise, quite literally, with a straightforward empirical and theoretical investigation. The authors ask two deceptively simple questions. First, how do we efficiently assign a unique perturbation to every example in a mini-batch, without destroying the computational efficiency of batched matrix multiplication? Second, do sophisticated noise parameterizations, or averaging multiple perturbed gradient estimates, actually yield meaningful gains over simpler alternatives? Their answer is clear: simplicity suffices. Isotropic noise with a single perturbation per update step recovers the vast majority of the benefits, and more complex schemes offer only marginal returns at significantly higher computational cost. Let's break down why this matters, how they achieved it, and what it means for how we actually train models. To understand the baseline, we need to look at what parameter noise injection does mathematically. When we inject a random perturbation z into our parameters theta, we're no longer optimizing the raw training loss. Instead, we're optimizing the expected loss over the perturbed parameters. In formal terms, that's the expectation of the loss function evaluated at theta minus z, where z is drawn from some distribution. What's elegant about this formulation is that this expected loss is exactly the convolution of the original loss landscape, with the probability density function of the noise. Convolution is a smoothing operator. By averaging the loss over random perturbations, we effectively blur the sharp valleys and isolated local minima, creating a smoother optimization surface that stochastic gradient descent can navigate more reliably. The standard implementation of this, often called noisy SGD, samples a single noise matrix per batch and applies it to all examples in that batch simultaneously. It's computationally cheap, but theoretically suboptimal. If we could pair each training example with its own independent perturbation, we'd explore the smoothed loss landscape much more thoroughly. The problem is that neural networks are built on batched linear algebra. A fully connected layer computes x times w, where x is a matrix of batched inputs and w is the weight matrix. If you want unique noise, per example, you traditionally have to loop over the batch, compute xi times w plus zi for each row, and that completely kills GPU parallelism. You trade theoretical elegance for practical efficiency, and most practitioners just stick with the batch-level noise. The authors of this paper sidestep that trade-off by exploiting a distributional identity specific to linear layers. Here's the core insight. Suppose we have a single input vector x and a weight perturbation z drawn from an isotropic multivariate Gaussian distribution. When we compute the product x times z, the result is still Gaussian. But its variance isn't constant. It scales precisely with the squared L2 norm of the input vector. In mathematical terms, x times z follows a Gaussian distribution with mean 0 and variance proportional to sigma squared times the squared norm of x. This lemma is the key to their efficient noisy SGD algorithm. Because the noise distribution for each example is just an isotropic Gaussian scaled by the input norm, you don't need to sample a separate noise matrix per example. You can sample one isotropic noise matrix for the entire batch, multiply it by the weight matrix, and then scale the resulting noise vector for each example by its input norm during the forward pass. The matrix multiplication stays fully batched. The computational overhead remains constant. But mathematically, you've achieved true per example perturbation. They extend this to biases by scaling with the square root of the input norm squared plus 1, which accounts for the bias term's constant contribution. The result is a training loop that explores the smoothed loss landscape more effectively, without sacrificing a single cycle of batched computation. Now that we have an efficient mechanism, the real question becomes, how much noise do we actually need, and how complex should its parameterization be? The authors ran systematic experiments across image and text classification benchmarks. CIFAR 100 for vision, and AG News and IMDb for natural language processing, using fully connected networks and TF-IDF representations. They started by comparing their efficient method against the standard batch-level noise injection. Across a wide range of noise scales, the per-example method consistently achieved lower test error, confirming that true per-example perturbation genuinely improves optimization dynamics. Then they tested the number of noise samples per weight update. The theoretical framework suggests that to accurately estimate the expected smoothed loss, you might need multiple perturbation draws and average the gradients. The authors tested 1, 2, 4, up to 128 samples. The results were unambiguous. A single perturbation draw per update step delivered the best test error. Adding more samples didn't improve performance. It actually degraded it slightly while multiplying the computational cost linearly. This is a crucial practical finding. Most noise-based optimizers assume you need multiple samples to stabilize the gradient estimate. Here, the stochasticity of a single draw is enough, and the noise itself provides the regularization signal. Finally, they compared different parameterizations of the noise variance. Isotropic noise uses a constant variance across all parameters and training steps. More complex methods scale the variance using the moving average of gradient norms, the squared second moment from atom, or the inverse of atom's second moment. The hypothesis was that adapting the noise scale to the local geometry of the loss landscape should help. The data says otherwise. On CIFAR 100, isotropic noise achieved a test error of 0.6241. The best complex method, squared gradient scaling, achieved 0.6213. That's a difference of less than half a percentage point, achieved with significantly more bookkeeping and computation. On the text classification tasks, the absolute gains from noise injection were smaller overall, which makes sense. TF-IDF representations aggregate token frequencies into fixed-length vectors, producing an optimization landscape that's already comparatively smooth. There's simply less sharp curvature for noise to smooth out. But even there, isotropic noise matched or closely approximated the best-performing method, and no complex parameterization caused degradation at its optimal noise level. So what do we take away from this? Parameter noise injection is a robust, theoretically grounded technique for improving optimization and generalization. But the literature has drifted toward increasingly elaborate variance schedules and multi-sample gradient averaging without empirical justification. This work demonstrates that the heavy lifting is already done by the convolutional smoothing effect of the noise itself. You don't need to adapt the variance to gradient statistics. You don't need to average multiple perturbed forward passes. You just need, for example, perturbation, which can be implemented efficiently through input norm scaling, and a single isotropic noise draw per update step. For practitioners, this means you can drop a lightweight noise injection module into your training loop, tune a single scalar variance parameter, and expect consistent gains without the overhead of complex schedules or extra forward passes. It strips away the complexity that often obscures what actually works in deep learning optimization. The authors note that future work will extend this distributional identity to convolutional layers with weight sharing, which will be the next natural step. But for fully connected and linear-heavy architectures, the message is clear. The noise doesn't need to be complicated. It just needs to be present. And in optimization, as in many things, simplicity isn't just elegant. It's sufficient.